Hi, we are starting. I have the honor to represent Daniel Soudry. He's going to talk about resource-efficient, quantized deep learning.
Thank you very much. It's a pleasure to be here. Is it working? No? This one? Okay. Hello? Oh, yeah. Thank you very much. It's a pleasure to be here. I'll talk about several of my works over the years. I'll start with some basic background from 3 years ago, like ancient times, and then I'll go to the more recent stuff. So if you fall asleep at some point, you can wake up at the next part and see. Maybe that's interesting. Okay, so let's get started. Of course, resource efficiency is a major problem. GPUs are power-hungry devices, and it's hard to put them on resource-constrained environments such as mobile phones and autonomous vehicles. And it's also, we want to improve their efficiency so we can train neural network with smaller costs, meaning like memory, area, power, and speed to improve on all those fronts. And we have much to improve since the brain have, as people also mentioned in the previous lecture, brains are doing things much more efficiently, also in terms of energy, than current computational devices. Okay, so let's a bit of a background about quantized inference for neural network. Initially, when people trained neural network, they were using 32-bit. It's still quite common. And when you want to do a product of a matrix of a vector, which is the main operation you do in those, at least in the feed forward and feed backward paths in a neural network, it's a sum of multiplication. So if you want to do each of those multiplication in 32-bit, it costs a lot and also memory. So of course, if you reduce all those weights to plus and minus 1 and all the activation to plus and minus 1, it becomes much more cheap to perform all those computations. For example, a multiplication and plus and minus 1 is now becoming a XNOR operation, right? Instead of floating point multiplication, which is much cheaper to implement. Also, you have less memory. You don't need to store memory. Also, bandwidth is reduced. You can do speed up. This, for example, in GPUs, we found that we can redesign the kernels to get acceleration with binary weights and activations. And of course, the main advantage is you gain much better energy efficiency, going from 32-bit to 1-bit, for example, in this extreme, about 3 orders of magnitude if you design the hardware for this task, at least in the compute. Okay, and how do you do binarize weights and activation? So this is kind of the trick we had over the first paper we had on this subject. Actually, the second paper. So yeah, I forgot. There's another paper. Oh, so what we do during training, we store a high precision version of the weights, and we use only the binary version, the quantized version of the weights, when we train the neural network. So all the weights in the neural network are used as binary, but stored as floating points. And then we want to do a forward pass or inference in the network. We just do a multiplication of the neurons, which are binary, with the weights, the binary version of the weights, and then take the sign. So our activation functions are sign. And then we do all the operations here, only binary operations, except maybe the first layer. So all the operations here are multiplication of a binary matrix with a binary vector. And that's very cheap to compute using the XNOR operation and pop counts. Okay, and then the problem is that how do we update the weights? How do we learn those full precision weights? What is usually being done in neural network is to use gradient methods, like stochastic gradient descent. So we want to update the weights using a previous value of the weights minus some gradient of the loss. We're going down the loss. We want to decrease the loss. So this is a bit problematic. You can't really calculate a gradient of a discrete, discontinuous function. Here the sine function, because it's 0 always, except infinity at one point. So we had some approximation of this. The intuition here was that to take the gradient of this sine function, we just add some noise, and then we take the gradient with respect to the expectation of the sine with this noise. This is a uniform noise, so you can get some expression which gives you the derivative of a sine function. And then you can differentiate through the network with this sine function. It's called a straight-through estimator. It actually appeared before in Hinton's lecture notes. And we also added this clipping to the weight so they won't go too far. This helps with the performance of the network. Okay, so this is kind of really in a nutshell how to do a training of a quantized neural network. If you want to read more, you can read in this paper. Just to make sure we're all on the same page, now we're only focusing on making the forward pass efficient for the inference phase, but the training is still done with high precision. So the training is still not very efficient. Okay, so this is joint work with Itai Chobara, Matthew Kerberix, Rani Laniv, and Yoshua Benjo. And when you try to test this on small data set like MNIST, SVHN, CFAR, it was a few years ago, then we found that the network with the binary weights had similar performance as the network with the full precision if we increase the size of the network by about 3 times. And then if you test the same networks on larger data sets like ImageNet, and then you find that if you maintain the same size of the network, you have a decrease in performance from 73.5 to 60.5 approximately here in this model. But this is still better than older model like AlexNet. Okay, so if you want to have really efficient network, going binary might give you some decrease. It could be acceptable to you. But if you're not happy with this decrease in performance, in the accuracy, then you can increase the width of the network. Then you regain most of the decrease in performance. But still, they ask, okay, did I gain anything from going binary and increasing the width? So let's try to think. So we said that in terms of energy, at least of the compute, we are 1,000 times more efficient, right? So if we increase the width of the network times 3, we had 9 times more parameters, let's say 10. Okay, so we use an order of magnitude in number of parameters and computation if you increase the width by 3. So you're still left with about 100 improvement, 2 orders of magnitude improvement when you use binary neural networks. Okay, if you use the correct hardware. So, okay, that's kind of promising. That's why you might want to use low precision in your inference devices. And people are now using like 16-bit and going lower, 8-bit. And now, why is this at all possible? Okay, why can you use binarization? This is a very radical thing you're doing to neural network. You're quantizing. You take all the weights and you're throwing away their value, just you keep the sign on all the activation. Why is it working at all? So let's give you some intuition. If you have some random vector in high dimensions, you just choose some direction, and then you have another direction in random what? Sorry? Oh, yeah. You have a vector in another random direction. Then the angle between these two, if they're vectors, if they're independent, is about 90 degrees. It's very with high probability. Because in high dimensions, the probability that it will be similar in direction is very low. But if you take the angle between a vector and its sign, then anybody has a guess what will be the angle between those two vectors? Almost 37. Okay, so 37 is, you can do calculation, just Gaussian integral, and that's very significant. It's much lower than 90 degrees, which is what you have for 2 random independent vectors. So you have the direction of the vector is seemed to be maintained quite a lot when you do binarization. But you say, okay, but this is just for random Gaussian vectors. But if you check in actually trained neural network, like, sorry, why is this not okay? Trained neural network on CFAR and such, then you see that the angle is around 37. This is what you get from the theoretical calculation, this dotted line, and the actual histogram is concentrated around that value. So it seems that neural networks are kind of maintaining the original position, like a direction from the full precision values. Okay. Another question you can ask, okay, what about the scale? You're changing the scale quite a lot, right? You're doing plus or minus 1. Then for us, at least in the training, we have batch norm. So that's not that as important as you might think it is. And for the inference, we don't care so much about the scale because we only care about in classification at least, about which class is larger, okay, or the sign. But if you look at the scale, then as I said, it could change a lot, and there are quite a lot of other works that are trying to correct that, trying to calculate what is the best scale to minimize the mean square error, for example, and you can calculate this analytically. other works trying to train that scale, trying to find it. But the other works is saying that, again, that's not very clear if it's really necessary to find this scale. It doesn't improve performance always in some networks. Another question you can ask is, how does the depth of the network affect this quantization? So if you quantize more, the network, it becomes harder to train. So we did some analytical calculation. I'm not going into the details here because my student is talking about this today at the main research symposium. If you want, you can go and check. But the main thing is that we found an equation that gives us what is the depth we can train given the number of levels of quantization of the activation. So if your number of activation levels, the quantization levels of the activations is Q, bless you, then the maximum depth you can train is Q to the power of 1.82. Okay, so we had this calculation, and this seems to match well with the empirical results. So we get up to some constant factor, we seem to get correct the qualitative behavior. Okay, so wait, this is not the correct presentation. Somebody changed. I knew something was wrong. Okay, so I updated it. Okay, they didn't update it correctly. Okay, so I'm sorry, I'll give you the old presentation, but this is, now we'll talk about quantized training. Okay, so now you want to train the neural network, and you want to do it also with low precision to gain efficiency. Okay, so you want, and we kind of talked about how to do training so you can get inference to be with higher precision. Now we would like to improve the efficiency during training itself. So we'll have lower energy consumption when we train the neural network. So again, we use low precision to do so. But a main bottleneck in training is batch norm. So batch norm is an operation, we'll soon explain, that is very sensitive to using a low numerical precision. So let's talk about that. Okay, so batch norm is an operation which is you take the input of a neural network, you subtract the mean and divide by the standard deviation. And if you want to know what this averaging is about, then this is the average over the mini batch and the weight, height and the width of the filter. Okay, so you average the input over those dimensions. And you can write this if you want some scaled L2 norm, this normalization will be useful for later. But this batch norm operation is very useful because it allows us to train a deeper neural network and do it fast with better final accuracy. It has a lot of empirical benefits. It's not really clear why is it so important, but it seems to be quite useful. So this neural network is this operation is very important to improving performance in neural networks. So we would like to find a way to make it work also with low precision, which is not working very well. So as we said, this is just batch norm is you subtract the mean and do scaling with this L2 norm of the input. And you might want to say, okay, so this L2 norm contains a square root of a sum of squares. So you need double precision to have a good performance there. But if you use L1 norm or L infinity norm, then you can get a more robust operations. These are much easier to use when you have a low numerical precision. So the idea is that we can use a certain scaling constant to change those norms, so we'll have a similar performance as this L2 norm. What do I mean by that? So we have two norms. We have the L2 norm and the L1 norm, which we want them to be similar in some way. So we'll say, okay, at least we want them to be similar in expectation on average. So we take the expectation of those two quantities and we want them to be the same. So we know the mean of those quantities here, the x minus the mean is 0. And we now can try and do some calculation of this expectation if we know what is the distribution of x. So we can make a common assumption that x is has a Gaussian distribution due to the central limit theorem because it's a sum of many inputs. So a sum of many variables is a Gaussian. And then you can calculate this constant, which gives us the exact ratio between those two quantities. So the square root of pi over 2 which is 1.25. So we just multiply our L1 operation by 1.25, and it seems to, for some reason, completely fix the problem. So if you just look on the accuracy of the neural network or the error, we see that if we don't use this constant, the regular L1, there is an accuracy degradation. But if we use this correct normalization, it gives us the same performance as the L2 batch norm. And you can also check this on other model, on ImageNet, ResNet 18 and 50. There doesn't seem to be any difference between the two operations. So just adding this small constant of 1.25 seems to fix all our problems, which is nice. Now, what we can do, you can try to reduce the numerical precision of the neural network. So, so the L1 batch norm, we can, if we use it, we see in this this graph that it performs the same as the standard L2 batch norm, with where you use you use 16-bit for the regular batch norm. It doesn't work at all. It's floating point 16-bit. But if you use 32-bit, it works. But in the L1 batch norm, if you use floating point 16, then it works the same as the 32-bit standard batch norm. So it seems that we can decrease the numerical precision with no cost. And we can even go further and train with integer 8-bit, almost the entire network. We can do a complete 8-bit operation for all the bottleneck operation in the training of a neural network, and get the similar performance as the full precision training for this ResNet 18 ImageNet model. Okay, so it seems that now, after we got rid of this batch norm and some additional tricks for the gradient, I will not go into here, we can make training efficient also with low numerical precision. Okay, so now we'll go back to inference. Okay, so now we wanted to do again inference of neural networks. We want to just train the neural network so it will be efficient for the inference phase. So how do we do it? Now we have originally had a neural network where we to get the good performance for inference, we quantize them all by training on this classification model we had with full precision. We're training it using quantized training on some data set, say ImageNet. And this gave us a quantized model, which now we could use. But what happens if we don't have access to this large data set? We only have some small data set, which could be even unlabeled, and we want to train the neural network to be quantized. How can we do that? Or just quantize the neural network. So to do so, we perform an operation called calibration. We look on all the tensor neural network. Tensor mean weights or possibly activations, and now we want to quantize them. So we have a lot of different values we get for all the weights or activations, and we want to find the best way to quantize it. What do I mean by quantize? So dividing the quantization, dividing the space into bins. So each time we had a full precision value falls in a bin, we replace it with the quantized value. So now we need to select the parameters of this quantization. Specifically, if we use efficient uniform quantization, the main parameters we have is the size of the area which we quantize. So we'll have a parameter alpha, which is this parameter which gives us the clipping value for the end of the quantization. Everything which is above this value is clipped to this value or minus this value if we're below. And we want to choose it. So what we'll do, we'll calculate the error for doing this clipping and all the quantization. So the error, if we're above this region, the error is x minus alpha. We're quantizing to alpha, and then we're calculating this integral over a distribution of all the values to get the error from that part of the tail. We can also do this for the other part of the tail. And we have an error term for each one of the quantization bins. What is the error from quantizing each bin? And we sum over all bins. So now we have a way to write the mean square error over all possible error cases. And now we can write the mean square error as a sum of all those terms. And now we want to calculate it. to do efficient quantization, we need to do some assumption on the distribution f, the function we're using in this integrals or expectation. So this function, you can make several assumptions. For example, if you use Gaussian assumption, you get some result. You can use a Laplacian assumption, which will give you another result, which is actually better empirically. And now you can optimize. You can try to differentiate this and optimize and get the optimal alpha, the clipping value, which give you the minimum mean square error. Note that the expression is determined by sigma, which is the variance, which we need to calculate. We do so using a small amount of data, okay, using unlabeled data. So you can now try to also improve additionally in the network by setting a different numerical precision for different different channels in each layer. So you can, using the same type of calculation, you can also derive what is the optimal number of bits you can put in each one of the channels to get the minimum square error. Okay, how to optimally allocate your bits given several channels in one layer. And you can also find this analytical formula. And another thing which we found to be useful for this type of post-training quantization is to subtract, to normalize by the mean and standard deviation of the original distribution. So the main problem is when you do quantization, you're changing the mean and variance of the distribution, the quantization operation. So this is an operation which corrects that, and this seems to improve performance quite a lot. Okay, and we can try now to assess how all those terms are contributing to the different types of networks we're checking, and we see that if we add beta allocation for the activations and bias correction, and this ASIC, which is the clipping optimally chosen clipping value, and then beta allocation for the weights, we see each of those methods is improving incrementally over the previous method, and essentially in the end we're getting very good performance for 4-bit and somewhat degraded performance for 3 bits. Okay, so it seems that for 4 and 3 bits we're getting much better improvement than what was before. Okay, and to summarize, it seems that we're getting quite a lot of improvement and almost back to full floating point precision in some of the cases. Okay, it's like a degradation of 1% or 2%. Using just this calibration technique of setting correctly the clipping values and changing the mean. Okay, so thank you for your time. Yes.
Number one is the training of binary.
Yeah.
I looked at it at the graph for slide 16. There were some glitches in there.
Where? Which?
16. If you look at the red on the right,
Yeah.
between 70 and 80, you see some glitch. The
Yeah.
question is it more sensitive to convergence, given that it's a binary network?
I don't think this graph was more sensitive specifically for this model. For other models, more complicated, deeper models, 50 you get some degradation in the some 1% or 0.5%, I think, for the last final error. Do 8-bit training. I don't think the training itself is more sensitive. Like you have those glitches quite a lot, even in standard training. Depends on hyperparameters.
My second question.
Yes.
Do you try ternary networks?
Yes.
And see if you get some.
Yes, it improves. If you, of course, it depends on your setting. What is the sweet spot, right? What is the hardware you have? What type of network? For example, for a current neural network, it's much harder. So it seems their binary doesn't work very well, and the smallest you can do is ternary, for example. Okay, so again, it depends on the type of networks, data sets.
Ternary on the data, ternary on the weights?
On the weights and activations. The data, weights and activations.
Activation.
Yes. Yes.
Do you need a specific hardware or framework for leveraging computation?
For leveraging it to the max, yes. If you want to have the best, then yes, you need a specific hardware. But even a standard network like GPUs, you can write kernels that do the operation more efficiently. You can combine together many operations in one. You take a lot of XNOR, like one register, and do it a lot of XNOR together. And we got speed ups like 7 to 13 times.